Okay, so, dang, did I delete it? I sure did it? Crap. Or did I write it on another? No. Oh, well, I deleted it. Okay. All right, so number 28. All right, number 28. Make sure it's going right. 28, and of course this is on page 125. All right, we got a 22 caliber rifle bullet traveling at 350 meters per second, strikes a large tree and penetrates it to a depth of 0.10 meters. All right, so let's draw a tree. See if I can draw a tree here. I don't like the way it looks. All right, so we got a tree here. Close enough, all right? And we got a dude over here with a rifle. He's a tree killer. Okay. There's the trigger guard. All right, boom, bullet comes out and impacts into the tree. Okay. And that depth right here is 0.13 meters, okay? That depth right there. So that is what? Delta X. So delta X is 0.13 meters. The initial velocity of the bullet, that's B right there, is what? 300 and what? 50? Yeah. 350 meters per second. What's the final velocity of the bullet? 0. Very good. 0 meters per second. All right. Okay. The bullet has a mass. Mass of bullet is 1.8 grams. Well, we know we need that in kilograms, don't we? 1.8 grams, which is equal to 0.0018 kilograms. Right? 3 places to the left. Yeah. All right. Assume a constant retarding force. How much time is required for the bullet to stop? So we got to find time. Okay. And what force in newtons does a tree exert on the bullet? So we want to know force of tree on bullet. Okay, question mark. You got to be kidding me. Oh, dear Lord, help me. Yes. I meant to hit a race and I hit the dead blank. All right. I wonder if we can do auto. No, there's no undo, is there? Control what? Control Z. Nope. It's gone. It is toast.
It's gone forever.
Yeah, it's gone forever. All right. Bullet. Sorry about that. Okay. 0.13 meters. Velocity's what? 3 what? 350. I don't know why they put it right. 350. That's initial. Final is 0. All right, the mass is 0.0018 kilograms. Darn pen don't want to work. We got to find time, and we got to find the force of the tree on the bullet. Okay, question mark. All right, now. Okay. Okay. So, how in the world do we find this? How do we find this? All right, you know we're going to have to include some kinematics because what? Because we're looking for time, right? Okay, we're looking for time. Okay, we have what? We have delta X. Oh, come on now. Delta X is equal to what? 0.13 meters. All right, look at your first 4 kinematics. We should have one that looks like this. Come on now. We should have one that looks just like this right here. V initial plus V final divided by 2 times the time. Actually, it could be written x final is equal to x initial plus, it could be written that way also. And so we solve for time, and it becomes what? 2 delta x, what? It becomes 2 delta x divided by initial velocity plus the final velocity. Is that right? Y'all check my math now. Okay? And so plug everything in. So we got 2 times 0.13 meters. Now again, where did I get that? I went back to my kinematics, the very first ones we did, those first 4. That right there is one of them. That right there is one of them. Okay? And I solve for time. And so that, and then of course initial is what? 350 plus 0, and that's meters per second. And we get a time of, real small, 7.43 times 10 to the, come on, pen, right, 10 to the negative 4th seconds. Okay? Now, does that make physical sense? Let me read it again. How much time is required for the bullet to stop? So think about from the time it hits the tree and stops. Does that make physical sense? It impacted what? 0.13 meters. Well, that's how many centimeters? That's 13 centimeters? Well, y'all, 30 centimeters is a foot. 30 centimeters is a foot. Okay, so 13 centimeters is going to be what? About like that. If 13 is a foot, well, there's 15. Well, there's about 13. So does that make physical sense? Bullets traveling at 350 meters per second. Are you kidding me? Yeah, that makes physical sense. Sure. Sure. That's how many thousandths of a second? 7 thousandths? Yeah. Yeah, that makes perfect physical sense. Now, if you'd have gotten a crazy number like 700 or even 7.4 to the negative 1, when, you know, you're saying 7, you know, you're saying, what, 7.1, that'd be to the negative 1, that's what, tenths? Yeah, no, it'd be less than that because it's a booking. Okay? All right. Okay, any questions on how I got that? Now see, y'all, it's important. Draw, label. Delta X, initial, final, mass, time we're looking for, and we're looking for force. Okay? Okay, what are we missing? All right, first of all, now that's A, right? That's A, right? Okay, B part says force, right? Well, what is force, y'all? How do we find it? MA? Yeah, MA, Newton's second law? Okay, well, we're missing something. We're missing acceleration, aren't we? Okay, how can I take a kinematic and find acceleration? Okay, but there's one problem with that. We didn't include our distance. You see what I'm saying? Change in velocity over change in time, okay, but we could take our change in velocity and divide it by the time. Will that give us the same acceleration?
That would just give us the acceleration within
That'll give us, yeah.
Within the tree, not.
Yeah, that would give us what? That would give us, yeah, within the tree. Well, let's see. Yes, because it's during impact. Yeah, okay. All right. So it's coming out of the rifle at 350 meters per second, and it hits the tree and impacts and stops. Okay. All right. So, but what are we looking for? We're looking for how much force the tree applied on the bullet. And the bullet moved through what? 0.13 meters of tree, didn't it? That's very important. That's very important.
So would that be the distance?
Yes. You remember this kinematic right here? Now solve it for acceleration. That term is gone because it's 0. And what do we wind up with? We wind up with what? Negative VI squared divided by what? 2 delta x. And so we get what? Now watch, that's negative right there. Negative on the outside. Negative. And that's 350 meters per second squared. Okay, so square it and then leave the negative. Divided by 2 times 0.13 meters. And we get an acceleration of what? Where the heck is it? Real small. Negative 4.7, negative 4.71 times 10 to the negative. Whoa. Not small, big, excuse me. Big, I'm sorry. Big. To the 5th meters per second squared, right? Now, does that make sense? The tree, and do we have to keep it negative? Well, we want to know how much force the tree is putting on the bullet. So the tree is slowing the bullet down. The bullet's moving this way, the tree's pushing back against the bullet this way. So it's in the opposite direction the bullet's moving. Does that make sense? Okay. All right, now we can solve it. Okay. We know the mass of the bullet, don't we? Because what do we know about Newton's third law? Whatever force the tree applies to the bullet is the same force that the bullet applied to the tree, right? Newton's third law. It has to be, y'all. It has to be. Okay? It has to be. It can't apply any more or any less. Right? Okay. So the acceleration then is what? We got 0.0018 kilograms times 4 and that's negative 71 times 10 to the 5th meters per second squared, and we get a force of what? Negative 847.8. Now that problem there kind of challenged us a little bit, didn't it? I'll give you credit. That one's a little bit challenging. Okay. I told you number 11, and that one was kind of challenging. Okay. We just have to think about what we're doing. We can't always use that standard equation. We can't always say, okay, acceleration average. Now remember, that's average, y'all. You did use it and it did work out. Okay, well I wasn't sure because I didn't try it that way. Sometimes you can, sometimes you won't. So you did use that one and it did still work. Okay, good. Okay, I wasn't sure if it would. I didn't work it that way. That's the way I worked it, okay? That's true. You're right. 350 is constant. You're right. Very good. So we could have used that one. Okay, very good. Very good. I didn't work it that way, so I went back to my kinematics. And that's fine. You can work it that way. Listen, I don't care. You can work it that way or you can work it the other way. Okay? So you get average acceleration. Sometimes you can work it that way. And since it was constant, it worked out that way. Very good. Okay? All right. And like I told you, there's more than one way to do these problems. Many times. Not every time, but many times, sometimes. All right, any other questions? All right. All right, who wants to work a problem or two? Who hasn't, by the way? Of course, let's not work 20. Oh, man. Where in the world have I marked? Oh, yeah, there it is. It's been a while since we've done this. 1, 2, 3, 4. Yeah, it's been a while. Been a little bit too long. Time's getting away from me. All right, don't be shy. You want to do one? Okay. All right, just whichever one you want to do, Wes.
I'll do 16.
Okay. And like I said, just roll the screen up if you want to. Oh yeah, let me stop this thing.